That's funny.
Come up to the first line and then just go through them so that they're on the...
Yeah, they'll do that. Right, but everybody's here. So the only reason you'd be watching this is if you missed something.
When you're playing backward sound effects.
Just for the record now, today is the end of June and it is 9:48. This is when Faisal left us and moved on to a better place. Yes. Newton's law. So what we missed when we weren't recording was a little bit of blah blah blah, followed by the important diagram of the gravitational field, something which you could draw in the exam. I also forgot to say, but I think you knew this already, those circles, what are those circles called?
Equipotential lines?
Yeah, equipotential lines, just like in the field. And we talked a little bit about how awesome Newton is and his formula again. And then what did we also talk about? The similarity with Coulomb's law. Right, now continuing. So we can simplify this formula a little bit. Well, not simplify, but expand it, I mean. We said F is force, G, gravitational field strength. Now, you notice I'm using the small g. That is not the same g as 9.81. That's the field strength. So if you want, you can just put a little e here, or a little s or something for strength, field strength. So how strong is the gravitational field? It's force per mass. Okay. Do we have a formula for force? Yeah. Now, we'll just use a big M for the Earth and the small m for the mass that's in the field, over r squared over m. And what happens here? The m's cancel and you're left with this formula for field strength. Field strength is, remember, newtons per kilogram. Let's calculate how strong the field is for Earth. What's wrong?
Were we supposed to write the definition?
Yeah, I'll go back to it.
Field strength is Newton per kilogram.
Yeah. Oh.
That's radius.
Oh, you're looking at this?
Yeah.
Well, the G has units as well. So
Okay. What's confusing me now? The gravitational field strength.
Yeah.
Is this?
Yeah.
And then
It's this or this. There's
Okay.
two formulas.
And then the
Both are in newtons per
What's the
kilogram.
F?
Newtons.
no the F, what's it called?
Force.
Of the field strength,
Just gravitational force.
gravitational force, and then strength of gravitational field. They're not the same thing.
They're nearly the same thing. It's just gravitational field strength is the strength of gravity per kilogram. Are we cool with this? Can you calculate the gravitational field strength for Earth? What things do you need to know? So right now,
Radius mass.
radius and mass. Right now, let's calculate the field strength we're experiencing. So I need to give you a couple of constants. So if you write this one down, the mass of Earth. Can you write this down? Mass of the Earth is 5.972 times 10 to the 24 kilograms. And the radius of the Earth, what?
Can you say again?
Yusuf, repeat.
5.972 times 10 to the power of 24. Yeah.
Yeah, you know, why are you confused? You know the number 24, don't you? Yeah. And the radius?
5, 6.
Go on.
So the 6 or a 5?
You tell me.
It's 6, 5 or 5, 6? 6, 5.
It's neither of these. It starts with 6, but it's 6,371 kilometers.
Mine is rounded up.
No, because then it'd be 6,4. 6,371 kilometers. I want everyone to calculate the field strength. G equals something, and it's newtons per kilogram. Tell me what you get.
637.
6,371 kilometers.
That's it?
I know, it sounds pretty pathetic, doesn't it?
Oh, the radius, okay.
Yeah. So,
I was like, what? Coming to here was like 4,000.
yeah.
Cute Earth. You want F or G?
I want G, and you can use the second formula here.
9.1.
Do you have a decimal point?
1.4.
Did you remember that the radius is in kilometers? There we go.
G.
The radius is in kilometers. You need to change it into meters. You did? Did you square?
Yes.
What's the constant for the G?
39.
G times
1.13 10 minus
9.82.
So rough.
Oh.
6, 7, 1, 0, 0, 0.
What? Oh, what's the constant?
Why do you use
9.81?
Oh, it's 4.
Don't know.
9 points.
Dun dun dun! So it turns out the gravitational field strength is the same as the acceleration due to gravity. Interesting.
What is it? Times 10 to the power of 12.
You have a mistake.
You have a mistake. Now, why did this happen? Watch. Here is 1 kilogram. So, let's calculate the force. The force is equal to the weight, which is equal to mg, but if m is 1, that's equal to g, which equals 9.81 newtons. So you have 9.81 newtons of force per 1 kilogram. This is the gravitational field strength, which is also the same as the acceleration. So, the g here actually has 2 meanings. We can think of it as the acceleration or as the force per kilogram, which I think is interesting.
So this G is always constant.
No, the g, as you can see,
For Earth, let's say.
well, no, because it depends on your distance from the center of the Earth.
Because there's a radius in the ball.
Because there's a radius, yeah. Okay, so make sure you have these down, please, and we'll continue. You got that?
Okay. The equipotential lines.
Hmm.
Okay. I wanted to ask this. Let's say Earth has the gravitational,
Yeah,
and then it's attracting an object
Yeah.
from space, and then this object has its mass, and then it's attached to the Earth.
yeah,
So when this object is now attached to the
yeah,
Earth, is it considered as a part of the Earth?
yes,
So the masses add up.
yeah, and the field increases.
Increases.
Yeah, yeah,
Nice.
yeah. Okay, continue.
So if more objects from space
Yes.
come to Earth, and then all these shooting
Earth
stars
will
and
explode.
everything, and then the gravitational field strength of the Earth will keep on increasing and
Yes.
increasing.
And the universe will
So
Yeah,
one
that's
day,
it, yeah, yeah.
the Earth will change its thingy because of the gravity increasing.
Change its thingy.
Its orbit.
The orbit's already changing right now.
Yeah, but like, it will change outrageously.
Yes, it will
Or
change.
it attract something and then...
Calm yourself down.
no, I'm just realizing so many things right now. Because like,
Down, please.
no, see.
What?
According to the Quran,
Who?
our book, our holy book in Islam.
Oh, sorry, Quran.
Yeah.
Sorry, I thought you said Dr. Anne.
Anyway.
Like, according to Dr. Anne, I was like,
Okay.
Dr. Anne.
The-
Actually, that's going to be my new name for the Quran now. Right,
Okay.
Go on, according to Dr.
Judgment
Anne.
Day
Yes.
will be like, what will start happening is that things from outer space will start to get in our Earth, and then everything will start exploding and those kinds of things.
Sounds like a good movie.
Yeah. No,
No, the thing is, seriously though, just talking about motion of planets.
Like this might actually happen one day.
There's a result in physics, a very important result, proved about 120 years ago, called the three-body theorem, which is very, very interesting, related to what we're talking about. If you have two bodies, like for example Earth, Sun and Earth, or whatever it is, two bodies is a stable system, and they can continue like this forever. But the moment you have three or more bodies, which could be simply Sun, Earth, and Moon, or other planets too, then it's unstable, which means that it will continue in orbits up to a point until then it collapses then. And that's kind of already happening. It just happens slowly. So what's happening right now is, yes, the Earth is going around the Sun, obviously, but it's not in a stable circular orbit because there are more than three bodies in the solar system. Its orbit is increasing. I can't remember the distance, but each year it moves further. No, sorry, I apologize, I have it backwards. The orbit is decreasing. And likewise the Moon.
We'll get in Sun one day.
So the climate change essay.
Yeah.
The Moon.
It's not caused by humans.
The Moon's orbit is increasing each year, so the Moon is moving further away from us. So obviously at some point it reaches a level where out goes the Earth. No, sorry, in goes the Earth, out goes the Moon.
The moon's just gonna be like, yeah. Adios.
So long, suckers. As the Earth is spiraling into the Sun. Yeah.
Yeah, that's my
the
cue.
sun before the
Huh?
won't the moon hit the sun before the
No, the Moon is moving away from the Earth. Yeah, well, possibly it will. Yeah. The motion is described as chaotic. It's difficult to predict what ultimately will happen. You would need very, very advanced computers to predict the motion.
Or just leave that alone.
Yeah, there's some motions of immortality.
Yeah. There's that too. You let me know how that works out for you. Right. So, just to recap what we have said so far, all masses produce a gravitational field which attracts other masses. The force is found by this Newton's law we have. Fields always point towards the centre of the mass. What if the field pointed away from the mass? What would that mean? Which we don't have anti-gravity, which we can't do. Okay? The field around a small mass can be ignored. That's what I was saying to you earlier. Because masses are positive, the fields never point out, but only point in. No negative masses. The strength of a field can be given by this formula, and this in fact is the acceleration due to gravity. These are all things we said so far. The value of G near the surface of the Earth is 9.81. Again, we have said all this. So we've actually, although it's only been a couple of slides, we've actually said a lot. And now potential energy. And you could probably figure out the formula from the Coulomb's lesson. So thinking about Coulomb's lesson, what do you think the formula for potential energy is for a mass trapped in orbit, like the Earth around the Sun?
G.
Yes?
M1, M2 over R.
square
So close.
root.
No, yeah, no. I
So
stand
close.
by my answer.
Do you?
Minus G.
There we go.
M1,
There
M2
we
over
go.
R.
Minus. Yeah. There we go. Okay, please write this down.
Why did I say that? I'll have to go and delete and no.
Okay, I'll give you a potential energy calculation now. Do you still have the mass of the Earth from earlier?
Yes.
Yes. Okay. So here's the question. You are an intergalactic super being. Let's say Galactus or something like this. And you would like to remove the Earth from its orbit around the Sun.
Whoa.
Yeah. It will require some energy. Let's calculate how much. So what information do you still need to know? You know the mass of the Earth, which is small m.
What is my mass?
Make
Huh?
up your own math.
No. We have mass of the Earth. We need mass of the Sun. Okay, so mass of
Why
the Sun. Because we're looking at removing the Earth from the Sun's orbit. Yeah. And we need that too. So can you write this down? Mass of the Sun is 1.989 times 10 to the 30 kilograms. 30.
1.189.
1.989 yeah, and what else do you need? The radius of the Sun, the Earth's orbit around the Sun, and that is 940 million kilometers.
Yeah.
That's small.
940 million kilometers. I'd like to see you run that.
That's small.
Yes, I
It shouldn't be here.
bigger.
That's half of the circle.
940 million.
Kilometers.
Kilometers.
So that's 940 billion meters.
1.98.
Yeah, I knew that's
It's when I was using the word million, it's like lame.
1, 2, 3, 4, 5, 6, 6, 6, and 6, 12. So 940 times 10 power 12 meters.
No.
Because it's
10
kilometers.
power 9.
About 9.
9.
Oh, kilos just 3.
Yes, we haven't changed that.
Okay.
How much energy does Galactus require to remove the Earth from... What is, I'm pronouncing it right, am I? Yeah? Yeah. What's Galactus? You all know who Galactus is, don't you?
Of course they won't.
I'm shocked by this. How old are you? You're 17, aren't you?
Almost 18.
Yeah, you're supposed to know who Galactus is at this age in your life.
940 0 0 0 0 0 0 0 0
0, 0, 0.
Galactus.
Wong, the question is, how much energy is needed to remove Earth from the orbit around the Sun?
Do you know something?
Can you say again the R?
940 million kilometers. Million. You have an answer? Right, let me type it in. What was the mass of the Earth, please, did I say?
5.972.
972 times 10 to the...
24.
And the mass of the Sun?
1.989 times 10 to the power 30.
And then the distance we have, which is a square, is 940. That's how many meters? So Galactus needs about 10 to the 43 joules.
We, both of us, did not get this.
Did I type it in wrong?
Why is it 6.
Oh, no, sorry, I screwed up with my G. Dun 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 dun. Whoop.
Why is it square or even?
Yes, I screwed up twice. All right, leave me alone. We all make mistakes, okay? Had a little accident. There we go. Better?
Yeah.
8.4, like as if you never make a mistake. 8.43 times 10 to the 32 joules. That's a lot.
Galactus can do it.
Galactus can do it, yes.
What did you say the units were? Kilojoules?
Joules. Just joules. 6 is mega, 9 is giga, 12 is tera. How far can we go? Let's see. Physics. We can go as far as... No, we can go past tera, can't we? There's more than tera.
I think you can get to 32.
Do you think?
I think.
Full list. Give me them all. Oh wait, hang on. Oh yeah. No.
Whoa. Okay, how many do you want?
32.
3, 6, 9, 12, 15.
I can only get to 18 here. Exa.
Yeah, same.
18.
Yeah. Exa. Exa.
Hang on. I'm thinking how to write this answer. Okay. So if I divide by 18, this is exa. Hang on, now we can't really say exa in English.
Yeah.
So we have to use a different word. So million is 6, billion is 9, trillion is 12.
Let's use the one right before it.
Trillion is 12. No, not billion. Okay. 15. Okay, so it's about 1 quadrillion exajoules.
Satisfied?
Yes, very, very satisfied now.
Do you know what the dark side is?
Don't have that so much yesterday.
No.
You don't know dark side. You don't know Galactus.
Okay.
It's not comics, it's culture.
What do you
Everyone
want?
knows
What do you
these people.
Do you want €2 for that?
Alright, let's continue. Now, here's an interesting thing to think about. Don't we have a formula for potential energy yet?
Don't.
Faisal?
Yes.
So that's, you wrote down the answer. Just only the formula on the surface there.
Yeah,
'Cause
but if I was to make this R equal to
H.
the radius of the Earth, then shouldn't this formula be the same as this one?
No.
Wait, again?
Why are these different? I mean, both give potential energy.
Yeah.
The height means the height above the surface of the Earth.
Here, yeah.
Yes.
So let's just say
make the height
H
the
is
radius.
let's just say the H is 1 meter. So then PE equals mg. But what if I just change this R to R plus 1? Then shouldn't I get the same answer? Or
Wait.
let's have a look.
You are. Because you have a big G.
Watch this. Now, there's a little bit of a proof, so pay close attention, okay? Here is the Earth. And here is a mass on the Earth. And let's say its height is h. Okay? Now, if we look here, it has potential energy. And here on the surface, it has potential energy. On the top, its potential energy is minus g, mass of the Earth, mass of it, over r plus h squared. And potential energy on the surface, what's the only difference?
MGH.
It's just going to be r squared. Now, when it moves from here to here, is it gaining or losing potential energy?
Losing.
What do you think?
Just one
Or maybe I should rather say gaining or losing energy, yeah?
Just one question.
Yeah.
Why is it R squared?
Thank you, Andrew. That would have saved so much pain later. Thank you. Is it gaining or losing energy as it moves from the higher level? Not in this case, because the energy left it maybe in the form of light or something.
Gaining.
Losing. It's potential energy.
Go
If
on,
I just have it here and then I grab it and move it to here, has it gained or lost potential energy? It's lost potential energy. Because if you think about it, when I move it down here, it has no potential energy.
See, that's the thing. According to the formula, if the H decreases.
Now you be quiet. I don't want you speaking from this point on until I write end of proof. It'll be good for you to see this uninterrupted. Don't say anything because you're not allowed to speak, just nod if you understand.
Better blow my mind.
Alright, and silence. Nod, please, if you understand. Nod. Yeah, okay. Now, it is losing potential. I'm trying to do this proof. You need to take
You
some
got my
attention.
back.
Watch carefully. So, we have said it will lose potential energy, and we want to work out how much that is. Now, when we have the calculation going from here to here, the potential energy it loses is mgh, because here it has mgh, and here it has 0. So the loss is mgh. You agree? Okay. So let's see if it is mgh. So this one is, which one is bigger, the top one or the bottom one? Well, we also have minuses in them. But let's not worry too much about which one is bigger, because if we have it backwards, it just means our sign is wrong. But I'm going to say that the bottom one is actually bigger because these are negatives, which I know sounds a bit weird. If I have like -3 and -2, the -2 is bigger. And this fraction which is bigger is the one that has the smaller denominator, which is this one. So the loss will be -gmm over r minus gmm over r plus h. Now, let's clean this up a little bit. That will be gmm over r plus h minus gmm over r. Now, there's obviously things in common here that we can take out. So, let's take some things out. We can take out gmm, and we're left with 1 over r plus h minus 1 over r. Okay? Now we want to simplify what's inside. And what I'm going to do is I'm going to divide everything here by r. So that will be gmm. Well, what I mean by that is I'm going to take out the r. So I have r 1 plus h over r minus 1 over r, like that. I just took the r out here. Now I'm going to say let x equal minus h over r. It's just a substitution, nothing fancy. So this becomes gmm 1 over r 1 minus x minus 1 over r. Now what's in common here? R is in common, so let's take that out. Gmm over r 1 over 1 minus x minus 1. If you think about semester 1 geometric lesson, you will remember that 1 over 1 minus x is the infinite sum of 1 plus x squared plus x cubed, etc. minus 1. The ones here cancel, and you're left with gmm over r x plus x squared plus x cubed, etc. However, h is very small, r is very big. H over r is very, very small, and a very, very small number squared is an extremely small number. These are so small they can be ignored. So you're left with gmm over r times x. But let's remember what the x is. We said the x is, what did I say that is? Minus h over r. We won't worry too much about the minus, so that's gmm over r, h over r, which is gmm over r squared h, which is gm over r squared h. But this is the definition of gravitational field strength. So this is mgh, boom. Yes. So it is the same formula after a little bit of a proof.
This is what you do in your life?
Yes, it is. Now, I wanted to do this proof because you'll all see this proof in first year physics, proving that the two formulas actually are the same. The only difference is when you look at the surface of the Earth, you can use mgh, and you can prove that the mgh formula is actually coming from the proper formula which we looked at. Now, I don't need you to write that proof down because it's definitely not on the exam, but I thought it would be good for your health and general education to see that proof. I hope I didn't disappoint. No, I didn't. Good. Okay. Newton's law of gravity gives us the size of the force between two masses. This force is one of the four forces of nature. Do you remember what I said the other three are? We have gravitational force, electromagnetic force. Remember the other two?
So much like each other.
Yes.
Positive and negative something?
Nucleic? What the hell
Does
is
it have like
nucleic?
inverse?
No.
Weak nuclear force and strong nuclear force. Okay.
Nucleo?
Nuclear.
Nuclear.
Newton's law of gravity is an example of an inverse square law. Now, please note the small value of g. Guys, listen. Gravity is an extremely weak force. What is pulling down on that cup?
God.
Gravity. What is causing the gravity?
The mass of the object.
The Earth's mass is the field caused by... Yeah, the gravitational field is pulling this down, and what caused the gravitational field?
Oh, physics is nice.
The Earth? How much mass of the Earth?
So much of it.
How much of it?
9.81.
Now, how much
Oh.
of the Earth is pulling down on this cup?
5.9.
Wait, listen, huh?
All of it.
All of it. All of the Earth. The
Yeah.
entire Earth is pulling down on this cup. And who is pulling up on it? And who is stronger? True. It's true. It's true.
That is profound.
Yes.
That is deep.
Yes. It's true, and this is to emphasize the point that gravity is a very, very, very weak force. And if you think about the formula, what was the value of G? 10 to the minus... Do you remember the power for G in the formula? 10 to the minus 11. And what was it for K?
It was a big number.
It was a big number, wasn't it?
8.9.
It was 10 to the... Yeah, it was 10 to the 9 versus 10 to the minus 11. That's a 10 to the 20 difference.
You're telling me those electrons have more spins than this Earth?
No.
Well, for their size, yes.
Well,
Much
makes
more.
sense,
Yeah. Yeah, but like, considering how small they are. Yeah. Now,
imagine making an electron this big. Just this big.
no, true. Like, I did remember reading an article once where it's what if the Earth was in a giant proton?
Bro, the possibilities.
And you know what the end result was? I'm not joking. Everything in the universe ended up being sucked to it.
Yeah, like.
Yes. It's extremely strong. So
Nice. This is what I want to do when I go home.
yes. So this actually is a mystery of the four forces. Gravity is unusual because it's so weak compared to the other three. It's even weaker than the weak nuclear force. It's so weak compared to the other ones. And it's not understood why gravity is so weak. Like, if you look at the four forces, they all are very strong, and gravity is extremely weak. Extremely weak. Like, 10 to the 20 is a huge difference. You know, the difference between 1 kilogram and 10 to the 20 kilograms, what did we say the mass of the Earth was? Was it even 10 to the 20? Or was it 10 to the 24, yeah. So the difference between 1 and 10 to the 20 is like the difference between a car and an Earth. Okay.
What's car?
A car that's about 1,000 kilograms.
No, not even a car. Way less than a car.
What did we say the Earth was? 10 to the 24.
Yeah.
So if I had 10 to the...
Oh yeah, 4. Okay, yeah.
Okay, about 10... A bus.
Yeah.
Yeah, the difference between a bus and an Earth
Yeah.
is the difference between how weak gravity is compared to the other forces. Okay, and it's quite strange for this. I mean, it's one of those things about physics where people don't understand why this is. So you can think about it two ways. Why is gravity so weak, or why are the other three so strong? You know.
What's an example of one of the other three?
The Coulomb's force between protons and electrons.
And
So
the other two?
that is what we're going to do in the next chapter, but just with an example,
There was an electric effect?
in that chapter we'll cover it.
There's a
No,
weak
no,
or
no,
a
no, no,
strong?
no, it's not related to that. If you look at an electron around a proton, the force caused by the charge, the force caused by Coulomb's law, is much, much, much greater than the force caused by gravity of their masses.
Yeah.
So it's as if they don't have a mass, a gravity force, compared to the other forces.
So the gravity between an electron and a proton,
Non-existent.
yeah,
Non-existent.
it's because of the charge that they're...
Because the charge is so big, the gravity doesn't even matter. Yeah. Okay, so here's a question for you to try. Yeah.
Best biospheres don't have anything this interesting.
Ah, no! Oh, they talk about blah 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 circulation, blah 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 immune system, blah blah blah.
I guess that's good for us, because if the gravity was strong, then...
Yeah, it'd be a bit of a problem, wouldn't it?
Getting off the bed would be really difficult.
Yes. But then maybe we would have just been built stronger.
Yeah.
You know, we could all, and then when we actually travel to a place like Earth, we'd all be like Superman, jumping over buildings. Gravity's so weak here.
Can we create chambers where the gravity is stronger?
Yes.
Nice. And make one day, then train in it. Like Vegeta. And then turn Super Saiyan.
One day, perhaps, Faisal. One day. I'm picturing now getting out bleach blonde hair dye. I'm going Super Saiyan, just a sec. I just have to let it dry. Give me a minute. Alright.
You watched Bleach?
Huh?
You watched Bleach? Oh.
No.
I thought
Just
you
talking
that's
about
Bleach.
Bleach,
Yeah.
like
It's
normal.
like,
Yeah.
oh, okay.
Right, try this one.
So
What is
you
the
are
force
cool for
between the
it.
Earth and the Moon?
This wouldn't be the radius, half of this, right?
No, that's the radius.
What is? The
No.
distance between the Moon and the Earth is the radius of the orbit. Calculate.
Your life choices and decisions. Nice.
What?
Nice. This is why I'm doing engineering.
Great.
So, this physics is so interesting.
7.6 times 10 to the power 28.
Double check. Say again.
7.6
Okay.
times 10 to the power 28.
Did you all get that? No. Okay, Andrew. Just double check.
Can you go back?
Just hit it on the calculator.
1,590.
We'll have confirmed that.
You're eating a lollipop.
So what? Leave her alone.
Can
Stop
you take
picking
that
on
myself
her.
seriously?
1.97 to that 20
Yeah.
to the power, times 10 to the power 20.
Oh, Andrew. Say again, Yusuf.
1.97 times 10 to the power 20.
What did you get?
Yeah, just never mind.
Andrew, this isn't a thing where you forgot that these are kilometers, is it?
No.
You sure? Remember the square?
Square.
Wait, why am I squaring?
Because you're looking for the force.
That's not potential energy.
This is the wrong formula.
Okay.
Why are you writing your zero?
Now, try this one. Dude! Try this one. How long does it take the moon to orbit the Earth?
A day.
No.
Yeah.
If you consulted Dr. Anne, you would know. Think about the calendar system you use.
Come on.
Forgot
Oh yeah, that's the time for the... Okay.
Like 29 days to 30.
Calculate. Try this one now.
28 days.
I thought,
How long?
yeah. Okay. How do you get time in this formula?
We've done this a couple of times. This is the sneaky F equals m omega squared one. The sneaky one. The one that you like. I know you like that one. I know you like it, don't deny it.
Okay, I started doing it. Don't solve it before I'm done, please.
Okay.
Omega.
Right, let's
That's the circulation.
This is just like
Yesterday.
Yeah.
I thought the moon would be lighter than this.
well, it's 100 times lighter than the Earth.
Yeah, but like it's way smaller and has nothing on it. Literally.
The Earth isn't heavy because there's lots of things on it, okay? There's so many Tesco's and Walmart, it's really weighing it down. Yes, Yusuf?
The formula is F equals m omega r squared.
No. M omega squared or. Dang.
3, 8,
Then what's the m?
5, 0, 0.
Which M? Oh, in the formula? Well, which is the one that's moving in this little story? Yeah. Finished? Got any more lollipops? Got any more lollipops? Did you really calculate it? Good.
What's your answer, Paul?
May I? Thank you.
Paul, what's your answer?
My answer, I think, is wrong.
Wong.
Huh? What's the answer?
No, sorry, Lee. Sorry.
What's the answer?
Sorry. Your answer will be in seconds. It should be ginormous. You'll want to convert it into days.
I got the negative answer.
Nice. So, how will we interpret that? The orbit of the moon is negative time. So, what does that mean? What would that even mean? It takes 1 second to complete. It takes minus 1 second to complete.
Oh wait, but that's the omega. Could the omega be the negative?
No. Well, not really. No.
How is this negative G?
Yeah. How did you get negative?
I don't know. Something wrong with my count.
We take the mass of the orbiting thingy, so the moon.
Correct. Wrong.
Huh?
I can't. Oh no, I got it. Thank you.
Yeah. And then
I think I just want to
Too many days.
Too many what?
Days.
Too many days? How many days?
Wow, wow, wow.
249
I
days.
think the omega could be negative.
Kilometers?
Do you remember your omega?
I see.
Omega.
No, I mean your work.
No,
Yeah,
it was
Oh, no.
squared
Up.
No. Okay, let's look.
Wait, I'm so close.
He just
Wait.
yeah.
How do I convert seconds to days?
Convert it into hours. Divide by 3,600, then divide by 24.
I got omega and I got 27.
3,600.
I got it really
And then divide by 24.
Yes.
27 days. 0.5.
I don't know how.
See, I wanted to ask you, this is why I lost that 1% in the math exam and didn't get 100. If the question asks how many days it takes, and it's 27.5, we round it up,
Yeah, I got 27.
or we round it down because it didn't finish a full day.
Or don't round it.
Yeah, exactly.
But like in a percentage question. No, but like in that question, you're getting...
Think about this. If I said, how many meters long is this room? And it was 10.5.
No, okay, how many people drink tea? And you get 27.5.
No, that's not comparable. Yeah, because you cannot have half a person, but you can have half a day.
Yeah, that's the thing.
Yeah.
That's why I lost a mark over there.
Yeah.
It was people, so I didn't round it up. And then you subtracted a mark from me.
No, because you should have rounded it up, wasn't it?
It was people.
Yeah, so you can't have half a person.
Yeah, so you round it down.
No, if it was 10.5 means you round up.
But you can't have a person, that's the thing.
I know, so you made a choice to round down, and that was the wrong choice. You should have rounded up.
Okay. So next time we get a question about the percentage, and it's a people, and then the percentage of people that go thingy.
Percentage is okay.
No, you round
Probability.
probability, yeah. And
No, Faisal, if it's more than 0.5 you round up. If it's
I
less
know
than
how to
0.5, yeah,
round.
so then why did you round down when it was more
because
than
it's
0.5?
people, because
So
if you're...
what if it's people? It's not like a different rule if you're rounding people.
Oui.
Congratulations.
Well, can you go back to the information?
We had this conversation. I know, I recorded it. I have proof. And I thought at the end of the conversation we were all satisfied. At least I was, and that's all that matters. Right, I see a few of you got the correct answer of 27 and a half days. Yeah?
So it's 27 or 28.
No!
It's
It's a 27 and a half days because that's how long it is. 27 and a half days. You can't, guys, you do know you can have half a day. Like that's possible. Right?
How many people drink tea? That was the question. The answer was 20 something 0.5. So it's like a half person cannot
You are right.
tea.
But
So
that's probability.
Yeah, and you rounded up.
Not down.
Not down.
Again, it's again.
Yeah, I think you've only repeated this point 4 or 5 times. Now, we won't do this one because I already did a potential energy calculation with you, the Galactus question. So there's no need to do that one.
enough.
Yeah. So these are the questions to work on. But before you work on them, I can read you a little article. The question is, what if the Earth was made entirely of protons and the Moon was made entirely of electrons?
Oh, this will be biggest explosion ever.
Well, let's read it there. So I'll read it to you. You might imagine an electron moon orbiting a proton Earth. Good idea. Sort of like a gigantic hydrogen atom. On one level it makes a kind of sense. After all, electrons orbit protons and moons orbit planets. In fact, a planetary model of the atom was briefly popular, although it turned out not to be very useful for understanding atoms. So, if you put 2 electrons together, they fly apart. Electrons are negatively charged, and the force of repulsion from this charge is about 20 orders of magnitude stronger than the force of gravity. That's actually 10 to the 20 I was talking about earlier. If you put 10 to the 52 electrons together to build a moon, they push each other apart really hard, all the electrons together. In fact, they push each other apart so hard, each electron will be shoved away with an unbelievable amount of energy. It turns out that for the proton Earth and electron moon in Noah's scenario, the planetary model is even more wrong than usual. The moon wouldn't orbit the Earth because they'd barely have a chance to influence each other. The forces trying to blow each one apart would be far more powerful than any attractive force between them. If we ignore general relativity for a moment, we come back to it, we can calculate the energy from the electrons all pushing on each other wouldn't be enough to accelerate all of them towards the speed of light. Accelerating particles to those speed isn't unusual. A desktop particle accelerator can accelerate electrons to reasonable speeds of light. So you know your old TVs, the one we were talking about that fires the electron? Those electrons are going at nearly the speed of light. So that's not too unusual. But the electrons in Noah's moon would each be carrying much, much more energy than in a normal accelerator. Orders of magnitude more than Planck's energy, which in itself is many orders of magnitude larger than energies we reach in the largest accelerators. In other words, Noah's question takes us pretty far outside normal physics and into a highly theoretical realm of things like quantum gravity. So I contacted Dr. Keeler, a string theorist at Bohr Institute, and I explained the scenario, and she gave me her thoughts. So she agreed that we wouldn't rely on any calculations. Okay, so let's get to the juicy part. There's a huge amount of potential energy in this scenario. We would blast the electrons apart. The energy warps space and time just like mass. The amount of energy in the electron moon, it turns out, will be equal to the total mass and energy of the entire universe.
Whoa.
Okay, an entire universe worth of energy concentrated into the space of our small moon would warp space and time so strongly that it would overpower the repulsion of those electrons. And then you get a black hole. And this is no ordinary black hole. It's a black hole with an electric charge. And for that you need different equations. Okay, you'd have a singularity, and where are we getting? Okay, oh, now here we get interesting. Wouldn't this black hole cause the universe to collapse? It's hard to say. The answer depends on dark energy. Nobody knows what to do with it. But for now, at least nearby galaxies will be safe, since the gravitational influence of the black hole can only expand at the speed of light. Okay, so it looks like
only our galaxy would be destroyed. The ones around it would be fine.
We're not. It's not 100% sure. At least the neighbouring galaxies will be sucked into the black hole, but possibly everything in the universe. It's 50-50.
Yeah.
So
would the black hole get stronger if it absorbs more things? Kind of like the gravity.
Yes.
So it keeps on getting
Yes.
stronger and stronger
Yes.
and stronger.
Yes.
Will it suck its own self?
And on that note, we